It is now time for us to move on to section 4.10. I hate to say 4.10 because that's not something we normally say, but in this case, section 4.10 talks about antiderivatives. Antiderivatives. Let's define what that means. Definition. A function, we normally use capital F now, is an antiderivative of the function f if the derivative of capital F is equal to f of x. So what this means is now I'm going to know what the derivative is, and I want to go backwards. Okay. Once again, I'm going to know what the derivative is, and I want to go backwards and see how I got there. Okay. That's what I want to do here. One very cool thing to note is that if capital F of x is an antiderivative of f of x, then so is capital F of x plus a constant. Let's think about why that makes sense, okay? Let's say f of x is equal to x squared. Well, as we know, the derivative of that is 2x. But if I have f of x equals x squared, let's just say plus 2, the derivative of that is also 2x. So the derivatives are the same whenever I only add a constant. Now, had I done like plus x, then it would be plus 1 over here, and they're not the same thing, right? But if I add a constant, just a constant, they're going to be the same thing. So what this means is if I know the derivative is 2x, if I go backwards, I have to make sure I say I could add a plus c there. So the common way I write these is with a plus c because there could be a constant there. So one more time, what I want to do here is I'm going to give you what the derivative is, and I want to go backwards and find how I got there. Okay? Let's look at some examples. Find the antiderivative of each of the following. The first one we are going to do is the function f of x equals 3x squared. So again, this is the derivative, and I need to go backwards and see how I got there. So I have to give this a good think and think about what function's derivative is 3x squared. Well, remember the derivative of x to the third was 3x squared because I would bring my power down, which would make it 3, x to the power now of 2. So how I got a derivative of 3x squared is I used x to the third. But remember, I have to do this plus c because there may be a constant there. So the antiderivative of 3x squared is x to the third plus c. Let's do another example. Let's say I have the function 1 over x. So again, what this means is I know the derivative is 1 over x. I want to know how I got there. Okay? So let's think about this. What function has a derivative of 1 over x? Well, we know from our rules that that would be the natural log of x. But once again, don't forget to add c. Again, I'm trying to go backwards. I know what the derivative is. I want to go back. Okay. Another example, let's do f of x equals cosine of x. Cosine of x. So once again, the derivative is cosine. I want to know what function's derivative got me here. Well, remember, we know the derivative of sine is equal to cosine. So it would be sine of x. But don't forget that plus c, because I could have a constant there. But what about if I said let f of x be equal to sine of x? And I want to know what function got me here, okay? Well, we know the derivative of cosine is negative sine, but this is positive. So the antiderivative, in order to get positive sine, must have been negative cosine plus c. Again, that is because the derivative of cosine is negative sine, but I have positive sine, so I've got to change my sign. One more example. Let's let f of x be equal to e to the x. And I want to know what derivative got me here. Well, as we know, e just stays e. So I got there by doing e to the x. But again, don't forget the plus c, because I could have a constant there. Alright, so that is what an antiderivative is. It is, if I give you the derivative, how do I go backwards? There is another term for the antiderivative, and that is the indefinite, or here, let me write definition first. The indefinite integral of a function is just the antiderivative. And once again, don't forget the plus c. And how I write that is with this lowercase sigma. That sign right there. The integral of f of x dx is equal to the antiderivative plus c. What this dx here does is it lets me know it's in terms of x. So it's a function of x in terms of x. If you go on and take calculus 3, we are going to have some where the function might be in terms of x and y, but I only want dx, which means I'm only going to worry about x. That's the point of this. Okay? But don't worry a whole lot about that right now. This just means it's in terms of x. So what this means is if I ask you to find the integral of sine of x, that's just the antiderivative of sine, which again we know the derivative of cosine is negative sine, so this would have to be negative cosine of x plus c. So this is just another way to write what we just did. So again, the integral of e to the x dx, we know the antiderivative of e to the x is e to the x plus c. Alright, so just like we had a bunch of rules for derivatives, we are going to have a bunch of rules for integrals too. Okay? Most of them we are going to learn in calculus 2, but there is one rule we can do now that's very helpful, and that is the reverse power rule, or the power rule for integrals. But like I said, sometimes it's called the reverse power rule. So it's the power rule we learned for derivatives, but backwards. Okay. So the power rule we learned for derivatives was that the derivative of x to the n, I bring n out front, so I'm going to multiply by n, x to the power of, I'm going to decrease this by 1. So if I want to go backwards, and I want to do the integral of x to the n dx, Since I decreased by 1 taking the derivative, I want to increase by 1 when I'm taking the antiderivative. I'm multiplied by the larger power here, which means I'm going to divide by the larger power there. So this is the reverse power rule. So let's look at some examples of that. Let's say I was doing the integral. Let's do one we already did. So we already did the integral of 3x squared, right? And we said we knew this was x to the third because we know that the derivative of x to the third is 3x squared. But we could also do this using this new rule here. So the 3 is just a constant, so that's just going to stay 3 times. I had x squared, but by my new rule, I'm going to add 1. So it was x to the power of 2. Now it's x to the power of 3 divided by my new power. So my new power is 3, so divided by 3 plus c. Well, what's really nice about that, 3's cancel out, so it's just x to the third plus c. Let's do another example. Let's do the integral of x to the 8th dx. Well, again, this is the power rule, but backwards. So I'm going to add 1 to the power. 8 plus 1 is 9. And then divide it by that new power, which is 9 plus c, which you could leave just like this, or I like to write it as 1/9 x to the 9th plus c, but that's just me. That's just how my mind works. It doesn't matter. Either one will be right. Let's do some more examples. Before we do that, actually, you know what? Yeah, let me do some more examples. Then I'll say what I was about to. Let's do the integral of, finding it in my notes, there it is, 5x to the third minus 7x squared plus 3x plus 4 dx. So now this looks really complicated, but it's really not. Basically, I'm going to do the reverse power rule for each term. Okay, so for the first term, we have a 5 times. My power was 3, but I'm going to add 1. So now it's x to the 4th over my new power, which is 4. Do the same thing for my next term, negative 7 times. My power was 2. I'm going to add 1. So now it's x to the 3rd over my new power, which is 3. Plus 3 times my old power here was 1. So I have to add 1 to make it x squared over my new power, which is 2. Plus, let's think about this one, okay? So the derivative is 4. So the function on how I must have gotten there must have been 4x. Again, because the derivative of 4x is equal to 4. Another way to think about that is just 4 is like saying 4 times x to the power of 0. So if I add 1, that's x to the first. So 4x. Either way works, however you want to think about it. But then remember, I have to do plus c. If you want to leave it just like that, that's fine with me. But I would write it as 5 over 4x to the 4th minus 7 over 3x to the 3rd plus 3 over 2x squared plus 4x plus c. If you want to check that, you can take the derivative of this and make sure you get that, if you want to. Another example, kind of like that one was, integral of x squared plus 4 times the cube root of x all over x dx. Now I wanted to make sure we did this one because it looks really hard, but I promise it's not, okay? First of all, I have the cube root of x. Remember, that's like saying x to the power of 1/3. So let's rewrite this as x squared plus 4x to the 1/3 over x dx. Now, since I have multiple terms on top, but only one term on the denominator, I can just divide each term in the numerator by this guy. So, that'd be integral of x squared over x is just x plus 4x to the 1/3 divided by the x to the 1/3 divided by x. I could do the power of 1/3 minus the power of 1, which is negative 2/3. So 4x to the power of negative 2/3 dx. So now I can just use the reverse power rule here. So that's going to be equal to, my power right here is a 1, so I'm going to add 1, and then divide by that new power. So x squared over 2, plus 4 times, again I'm going to add 1, negative 2/3 plus 1 is x to the 1/3 over my new power, which is 1/3, plus c. I can rewrite this first term as just 1/2 x squared. 4 divided by 1/3 is like saying 4 times 3, so that's plus 12 times x to the 1/3, plus c. So again, it's exactly like taking the derivative, but going backwards. Okay, so what I wanted to say a while ago, but I will say now, if you look in the PDF copy of the textbook, there is a really nice chart that lists out every derivative rule we have learned. Every derivative rule is on this left side over here. This is on page 489. Every derivative rule we have learned is over here. Now, what they've done is they have taken these rules we already knew and it changed them to integral rules. So just like we have the power rule over here, we have the reverse one over here. We know that the derivative of the natural log of x is equal to 1 over x. So the integral of 1 over x is the natural log. And on and on. It just takes every derivative rule and reverses it so that I have a nice chart of every rule right here. Again, this is in your book, page 489. So let's use these rules to do some more complicated examples that still really aren't even that bad. Example. Let's do the integral of 4 over 1 plus x squared dx. All right, so looking at this, there's not an easy rule I can think of off the top of my head, and so I'm going to look at my rules that I know on this little chart, and I'm going to see if there's any that look kind of like it. All right, so I'm looking through here. Oh, and look at this rule right there. We know from chapter 3 that the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared. Therefore, the integral of 1 over 1 plus x squared is inverse tangent. Now this looks almost like mine, except we have a 4. So all I would do is just multiply that by 4. So this would be 4 times the inverse tangent of x plus c. Again, because from our rules we know the derivative of inverse tangent is 1 over 1 plus x squared. So if I want to go backwards, that means the integral of 1 over 1 plus x squared is the inverse tangent of x. But since I have a 4, it's 4 times that. Another example, this one takes a little bit of manipulation. Integral of tangent x cosine x dx. Now, as I have it right here, there's not really a rule for tangent x cosine x, right? If I look at all of them, there's some trig stuff over here, but none of them have tangent x cosine x. So let's think if there's a way I can rewrite this, okay? Remember, tangent is sine over cosine, right? So let's rewrite tangent as sine of x over cosine of x times cosine of x. Now the reason that's helpful is because now if I look, cosine of x is going to cancel out. So this is just the integral of sine x dx. And we've actually done that one a few times. We know that the derivative of cosine is negative sine, but since I have positive sine, that means I'm going to get negative cosine of x plus c. Negative cosine of x plus c. While it is on my mind, there's something that I said a while ago that I want to correct myself on. We did an example of the antiderivative of 1 over x. We did it over here, the antiderivative of 1 over x. And I said we got the natural log of x. That's almost right. One thing we have to make sure we do is this has to be written as the natural log of the absolute value of x. And the reason why is because we know that the domain of a logarithm says that the inside of this must always be positive. So I'm going to take the absolute value to make sure it's always positive. So make sure you do the natural log of the absolute value of x. Okay, that's a big deal. All right, I just wanted to state that just really quick. All right, there's only one more thing we have to talk about for this section. Definition. A differential equation is an equation written in terms of a function's derivative. So basically, it's an equation where the derivative is a part of it, okay? So I could have the example of like 8y prime minus 3 equals 10. That kind of thing. Or like y double prime minus 2y prime plus 8 equal to 1. It's an equation where I'm working with the derivatives, okay? Once again, it is an equation where I am working with the derivatives. What I want to do when I solve these is I want to solve for what y is. Okay? I'm wanting to solve for what y is. There is a special type called an initial value problem. And what this is it is a differential equation with extra information so we can solve for c. Remember, we always put a plus c. These help us solve for what c is. Okay. Now we are going to practice solving some very basic differential equations. Like I said, very basic. If you like these, there is actually a math course a lot of schools have over this stuff. And I loved it. I took that class whenever I was a junior, and it was my favorite class. I loved it. So if you like this kind of stuff, take that class. But like I said, in here we're just going to do some very basic differential equations. Example. We're going to solve the initial value problem dy dx equals sine of x such that y of 0 is equal to 5. Alright, so the equation part is right here. What this says is the derivative of y is equal to sine of x. So I need to solve this for y. Okay? So what I really want to know is what function's derivative gives us sine. Well, like we've said a bunch of times, that would be negative cosine, because the derivative of cosine is negative sine. But I have positive sine, which means y is going to be equal to negative cosine of x plus c. Okay. Again, it told me the derivative, so I need to use it to find what the y is. Okay. Now I can't stop here because they gave me 1 point. They said when I plug 0 in for x, I get a 5. So I'm going to use that to solve for c. Okay. So they know whenever we plug in a 0 for x, I get 5. So 5 must be equal to negative cosine of 0 plus c. Again, because I plugged 0 in for x and 5 in there for y. So I know the cosine of 0 is equal to 1. So 5 equals negative 1 plus c. So to solve for c, just add 1. And I get 6 is equal to c. So the function y is negative cosine of x plus 6. Negative cosine of x plus 6. One more example. Let's solve the equation dy dx equals 3x to the negative 2 such that y of 1 is equal to 2. So I need to figure out what the y is. Okay. Well, I know from the reverse power rule what I can do is add 1 to my power here. I had a 3 times. Add 1 to my power here, which would make it x to the negative 1 over my new power, which is negative 1. So y must be equal to 3 divided by negative 1 is negative 3 x to the negative first plus c. So now I need to plug in this point. I know when x is equal to 1, y is equal to 2. So I have 2 equals negative 3 times 1 to the negative 1 plus c. Again, because we plugged a 1 in for x and there's 2 in for the y. Now I can use this to solve it for c. 1 to the power of negative 1 is equal to 1. So 2 equals negative 3 times 1 plus c. Negative 3 times 1 is negative 3. And then add 3. So 5 is my c. So we have y equals negative 3 x to the negative 1 plus 5.